Good day, physics class. Good day. Hope you're doing all right. I am coming to you from my house today. This is my back room. The window's shut. Let me open the window for you so you can see the glare from the sun. Well, it's not really the sun, glare from the glass and the gloomy rain. All right, hope you're having a good day. uh, you know, we're making it. I really hope you had a good senior trip. I hope you're adjusting to being home. I hope you'll really heed the advice of the medical professionals and stay home. It's really important to kind of isolate ourselves, keep germs from spreading. I hope you're praying for this situation. You might have some people that you're concerned about. I hope that you pray for them. I hope that you connect with them. I think we have a wonderful opportunity to connect with people via these different methods of FaceTiming or Zoom meetings. We'll probably set up a time to do some Zoom meetings, some Zoom classes as we move forward. So today our job is to actually keep talking about science. I've gotten a few of your homework assignments from yesterday. Well, from Monday, I should say. I don't remember. I think I'm going to post this video tonight, Tuesday night, Wednesday morning. So that'll be good. I hope you guys are getting things. If you have questions, please email me. That'll be a great way for us to stay in contact. We talked about some general thermal energy terms, and we talked about specific heat capacity in some previous videos. So I just wanted to go over some of those concepts. I really love the concept of specific heat capacity and how every material has a different capacity for absorbing, storing thermal energy. Every material is different. Every material is made up of different things, and their molecules are going to interact and do different things. So in that case, a chunk of metal is different than a piece of wood. Metals are conductive, woods are more insulative, which are terms that we know them from our electricity concepts. But the interesting thing is electrical conductivity and electrical insulation is very similar to thermal conductivity and thermal insulation. At least the types of materials that are involved in those concepts are basically the same. So as we're talking about specific heat capacity, a piece of metal has a low specific heat capacity, and we choose that metal for different purposes and use it for different things based on its capacity. Something that's insulative, we choose it for its specific heat capacity characteristics. One example that's very that you might consider kind of an insulative thing is radiator fluid for a car. It's got a higher specific heat capacity and a higher boiling point. That's why we use it in a car. We put it in a car to absorb the thermal energy from an engine that's highly conductive and gets really hot. The coolant absorbs that, and then we dump the thermal energy out through a radiator to control the heat in the engine. So the specific heat capacity of that material is very important. And so that's really kind of where this applies on the physics level. I'll try to stay away from the microscopic chemistry kind of level, but know that most of these things start off on that microscopic level. The way these things work and behave is because of their microscopic atoms, but we'll try to apply it to a larger scale, to physics kind of engineering kind of concept. Well, today we're going to move on and we're going to talk about thermal expansion. And I'm sure you have seen thermal expansion in some way. But what I've got a file, and I have the ability to share this screen with you. So I'm going to do that right now. And I believe you should be seeing a a Google Doc. It looks like a Word file, but a Google Doc that is about thermal expansion. Here's some main points about thermal expansion that I'll go through with you. I'll talk to you about them. And then I've got some illustrations and some YouTube videos and some places where you can see thermal expansion happening for real. I'll actually post this file to the LMS, and I will also post links so you can see these YouTube links that are in there. They're really interesting. And so you can watch those. So let's start talking about thermal expansion. Right? Thermal expansion, you can see it there at the top of this page, is the increase, or technically we can just say change, in dimension of matter due to the increase in the temperature of the material, or the decrease, because really we could talk about that in a very generic term. The change in dimension of matter due to the change in the temperature of the material. So essentially, right, what you have going on is the basic relationship is if you increase the temperature of something, it increases in size. And then the reverse is true. If you decrease the temperature of something, it decreases in size. And I make a little notation here that is for most materials. And I say for most materials because there are some where that doesn't happen. Technically, as you decrease the temperature of water, it actually does decrease in size, but you actually hit a temperature point where it actually reverses, which makes water so very, very unique and so very important to our world. But for basically most every solid and most other non-water-based liquids, you increase their temperature, they increase in size. You decrease your temperature, they decrease in size. That's the way that it works. And the changes, I hope you can see, I just kind of highlighted it a little bit here. The changes can be in length, width, height, volume. So if you had a square piece of material, its length would increase, its width would increase, its height would increase, and its total volume would increase because all those dimensions are increasing. But if you didn't have something that had, like a square shape, let's say you had like a cylinder, like a metallic cylinder, it would increase in length, but it would also just increase in, I like to call it girth, the size of it like that. So essentially its volume would be increasing, its radius would increase. Now each material will expand and change differently. And that's just due to the nature of the material. Now, we're not going to sit here and have a whole material sciences class and learn about this kind of metal, and then go to this kind of metal and then move on to other materials like liquids, or move on to carbon fibers and other things like that. That's, engineering school for you if you are choosing to get into that. That's, the science of aircraft aluminum and the materials that they choose to build aircrafts out of. So the expansion and the change that happens in materials is all based on the material. It might be affected by the density of the material, but there's not a guarantee that the most dense materials are going to have the most expansion, or the most dense materials are going to have the least expansion. It's not just about density, but the density can have an effect on that. The nature of the materials, right? How strong they are, how strong the bonds are. Some of those things are all going to play into it. There's multiple factors. Right? So you might have something that's really, really dense, but it has a low melting point and it turns into liquid very easily. Well, its thermal expansions can be different than something that's really, really dense and has a high melting point, and it's able to absorb more thermal energy, and those pieces of matter are able to expand and move more. Let me give you a basic example of that. Lead is very, very, very dense, but lead has a low melting point. You can melt lead with a butane lighter. I've done it. It's very easy to melt. So you're not going to notice massive changes in the thermal expansion there very easily because it's going to melt down. But something like steel, it's pretty dense. I don't think it's denser than lead. Off the top of my head, I don't remember. But it doesn't have the same melting point as lead. So it's going to have these thermal expansion changes that are different than other materials. So essentially what happens is the changes that are going on with the microscopic atoms, right? Because that's really what's going on. The microscopic atoms are affecting things. They change the macroscopic size of the material, or the large scale size of the material. And so this is really where you get a lot of interesting engineering applications. You have to know the condition of the object that you're trying to engineer and the conditions that it will have to exist in, and then choose the materials that can handle it. You have to build it, you have to test it, you have to refine it. For example, I have an old acquaintance who I'll say was an engineer. I think he's probably retired now, but towards the end of his career, he was actually an engineering manager. He managed a group of engineers. And one project that he was working on was a actual articulating fin that would move back and forth on a rocket, essentially a weapon system that was going to be launched off of a military boat or military plane or something like that. And so they had to design this thing from, from this idea given to them from the military to let's strap it onto a plane, test it out, and then if it works, let's manufacture it. And so they had to choose their materials, and they had to know what conditions those materials are going to exist in. Are they going to be in hot climates? Are they going to be in cold climates? Well, if it's strapped to an airplane, it could be flying from a desert base up into high layers of the atmosphere where it's really cold. So this device has to be able to handle temperature extremes. Does it have the ability to to expand enough or not expand too much to handle those temperature extremes? And so they ended up having to choose materials, design it, build it, test it, refine it, send it off. And then when they figured out all the best ways to deal with it, they turned it over to the US military. So what I want to do now is actually show you some really common places where you'll see thermal expansion. And some of these you've actually run into in your life. This right here, this picture, is actually finger joints on an expansion joint on a bridge. This is not the only type of thermal expansion joint on a bridge. I've seen others, but what you've got is you've got these fingers that slide back and forth as temperature changes. And so as things get hotter, the bridge, like the bridge portions actually will extend, and so those fingers will actually push closer to each other. And then as things get colder, the materials shrink and those finger joints will actually slip further apart. And there's a support system underneath those joints, but it allows the deck of the bridge to expand and contract with temperature changes. That's really important, because if you didn't have the ability to expand and contract with those temperature changes, you'd essentially have the buckling of the road system, which actually reminds me, my family is in Pennsylvania, the land of perpetual potholes and perpetual road work, right? Expansion and contraction is what causes pothole problems. So you have a little crack that forms in a roadway, and then water gets in, and then wintertime, that water freezes. Well, we all know that water expands when it freezes. Well, there's no expansion joint built into that crack in the pavement. So what happens is that water expands and just expands out, and it actually cracks the pavement larger. And then, it melts, more water fills in. If it freezes again, more water's in there, so it comes and expands it even more, because there's no expansion joint. That material is not made to expand. Bridges are made to expand with hot and cold. Potholes, they're just cracks in the pavement, and those do not have the ability to expand and contract. So what ends up happening is you get damage and cracks. Here is a YouTube video. I believe this YouTube video here is about bimetallic strips. There are these really, really cool bimetallic strips, and I actually have one, and I would show it to you. But honestly, the YouTube video will probably work out better than if I had brought it home and tried to heat it up right here in my back room. But a bimetallic strip has two different metals that are fused to each other. Typically, it's brass and steel. And so you can see two different colors on this, the brass and steel fused together. And if you heat it, they expand at different rates. And so what ends up happening is it goes from straight to curved, because one side is expanding greater and the other side is not expanding as much. And so what ends up happening is if it curves this way, the part that is curving away, that is the part that is expanding more. The part that's kind of got the cave side, that's the one that's not expanding as much. And then actually, when you let it cool, it actually comes back to straight. This is probably a better view, isn't it? No. I'll let you see the moneymaker. All right, here's another one. You probably haven't seen this, but I have seen it multiple times in my life. This is actually a thermostat for a heating and air conditioning system. And they're really cool. They have a liquid mercury switch, which turns them on and off. But the way that the liquid mercury switch works is there's actually a bimetallic coil in there. So if you look, you can actually see a coiling, what might look kind of like a coil spring, but it's actually a bimetallic strip. And as the house gets hotter, right, that bimetallic strip will expand and it will actually start to tilt the mercury switch this way. And as the mercury switch goes this way, it'll disconnect and it will turn off. And then as the house gets colder, it starts to contract and it will go this way. And then it will actually shift the mercury switch this way and it will touch the contacts and they'll turn on the heater. And so the heater goes on and off as the bimetallic strip lengthens or shortens due to expansion and contraction. It's really kind of cool. Now here is a really interesting example of thermal expansion. And in this case, the thermal expansion issue is really length, the girth, the other dimensions of railroad tracks are not a huge factor, but the length is a factor. There have been situations where railroad tracks have not been built with proper expansion capabilities, and what ends up happening is they end up having jogs and curves and buckles in them. And there's a little interesting fact here. This phenomenon resulted in 190 train derailments during 1999 to 2002 in the US alone. You typically don't hear about rail cars being derailed, probably because if it's not a passenger situation, we're not too concerned about it. You knocked over a car that's just hauling freight, not too many people get injured. But if it was a situation where people got injured, we hear about it. But they actually have to build expansion and contraction joints into the railway. And you actually can see expansion and contraction joints built into many, many roadways. You can even see it on sidewalks. Hey, I don't know what you guys are doing with some of your off time. My guess is you're not spending quite as many hours at schoolwork as you would be if you were in regular school. But go out, take a walk on the sidewalk. Of course, don't interact with people. We're supposed to isolate and keep the spread of germs. But look on the sidewalk. There are cuts or cracks, and sometimes there's even a squishy material that's put in between sections of sidewalk or in driveways or patios around a house. And that is for having some buffer zone for expansion and contraction of cement and asphalt, right? So you got to have those expansion and contraction joints. Now here, I should make this larger, but here is a picture of a glacier that shifted on me. Glaciers are made of, well, sorry, that's not a glacier. That is a, iceberg. Icebergs come off of glaciers. Glaciers are huge. Icebergs are big, but not as big as glacier. And the iceberg here is frozen water. And I mentioned this earlier, but water actually expands when it starts to get lower than 4 degrees Celsius, and it expands by about 10%. And so that's why our ice cubes float. Our ice cubes float because they've actually expanded and they've become less dense. And so we've already dealt with the concept of buoyancy. Less dense floats on more dense. And so you can see only about 10% of the glacier is sticking out. 90% of that, sorry, not glacier, iceberg. 90% of that iceberg is below the surface. And that's one of the situations where water is different than the main relationship of increased temperature, expand, decrease temperature, shrink. We've got water doing that oppositely when it gets below 4 degrees Celsius. But this is huge. I want to take a second and throw in a biblical integration plug here. This is the way God designed water to work. God made the earth to have seasons. I don't know about you, but I love the different seasons. Spring, summer, fall, winter. I love each one of them for different reasons. I do love the concept of winter. I like to be out in the cold and make snowballs, go sledding, skiing. It's fun for me. I know everybody is different, but when a layer of ice forms on a lake or a pond, we need that ice to float on top. Because if that ice was to freeze and become more dense and sink, it would trap life, fish, and plants underneath a layer of dense ice. And then the next layer would freeze. And if it got more dense because it didn't expand, it would sink. And so we just have this, in the really cold climates, we'd have this continual freezing of a layer of water and then sinking, freezing and sinking, freezing and sinking. And it would kill the life that's in that water body. But since water freezes and expands and floats on top of a pond or on top of a lake, right, then the lake water underneath can stay at a fairly constant temperature that's not too cold for the life to live, and it survives the winter, insulated by a layer of ice. God designed it that way. God is not he's not a fool. God made it amazingly. The next concept here is with gases. This is an illustration of a hot air balloon. And if you remember Boyle's law and Charles' law and Gay-Lussac's law and the combined gas law and ideal gas law from chemistry, this is no new concept for you. A hot air balloon has hot air inside of it. And so that hot air balloon, the molecules are hotter, they move more, they expand more, and they fill up the balloon. And essentially they make the balloon less dense. And so the colder, more dense air molecules outside the balloon kind of buoy that balloon up and it floats because the air inside is less dense, the air outside is more dense. And that's, thermal expansion of gases. And here is a YouTube video that I found that's really interesting. It's a little bit longer than it needs to be, but it's actually the filling up of a hot air balloon. They lay the hot air balloon out on the ground. They put a huge fan at the mouth of it and start blowing air into it. And then eventually they get it filled up with air, but it's still laying over on the ground because of this huge fan. And then they start firing the burners into it, and it erects the balloon straight up. So watch it. This one you can fast forward through it, hit it, and watch how the balloon expands, but you don't need to watch the whole 8 minutes straight because really what we want to see is where they fire it up at the end and make the balloon go whoop up. All right. So I'm going to stop sharing this screen and get the talking head to be a little bit bigger here. I hope you guys are doing well. If you have any questions about this concept of thermal expansion, let me know. I'll be glad to answer them. I'm going to try and keep connecting with you guys. I hope you are enjoying some of this school stuff via this different method. Keep in mind, it's not going to be like this forever. God has a plan and purpose, and we're just going to keep following his plan and purpose. All right. Have a good day. Mr. Hicks signing off. Bye.